Okay, so moving on to our next talk is Jarron Leisenring, who will be talking about the capabilities of the Imaging Technology Lab.
Okay, thanks. Thanks for the organizers for allowing me to speak, and happy to be here. Just on a really quick note, I'm excited that Pandora is coming to the Mission Operations Center because that mission was enabled by so I've been working on JWC NearCam for the past 10 years. And so that mission was enabled by us, or not really loaning, but giving them one of our spare detectors. So I'm really excited that all these connections. Okay, so, but now to switch my brain. So I'm the newly installed director of the Imaging Technology Lab. And I think you all are going to be seeing a picture of this applied research building quite a bit today. So we are located over at the ARB. I just want to tell you a little bit about what we do. Even though I'm new, the lab has been around for 25 years. It was originally founded by Mike Lesser, who recently retired, hence why I'm here. And so we're over in the ARB. We have a 2,000 square foot ISO 7 class 10,000 clean room. About 450 square foot of an ISO 8 wet chemistry lab, and then 1,000 feet of sensor characterization with cryostats and assembly and support labs. So we are an end-to-end production lab for imaging sensors, mostly dealing with CCDs and CMOS arrays, so UV, visible, near IR kind of capabilities. So we start from, we get the silicon wafers from a fab center, and we take it and move it through a process all the way to the end to produce a package detector that we deliver to usually astronomy instruments. But we do a lot of different things, Earth observing, semiconductor industry, and high energy physics. Just some notable projects that we've worked on over the years. There's way more, but these are some of the larger ones we've done. We did half of the sensors for Rubin Observatory LSST camera, which is the world's largest contiguous camera. Did 21 cameras we delivered to the Sloan Digital Sky Survey 5 large volume mapper. We not only packaged the detectors, we actually also built and delivered the instruments themselves. We are currently working on, well, we have done the detectors for dark energy survey, the blue channel, and we are currently delivering red spares for them. And then, a couple hundred sensors for the dark energy experiment and the biospectrographs. Another thing that one of the, like, as I mentioned earlier, we don't just work on astronomy. We've been partnering with a local company that does, electron beam microscopy. That was critical in the the mapping of the COVID-19 spike protein. So this was a really cool just side project that we were doing, and I went to a cryo-EM conference at ENR2 a couple weeks ago, and everyone was like loving these detectors. I didn't realize how much they really revolutionized that field in biological microscopy. But we don't do ground. We don't just do ground. We also do space. So these are a couple. We have 9 different sensors in space. One is this Epic at L1, and then a lightning mapper on the GOES weather satellites to sort of in real time map the lightning ground to cloud and cloud to cloud lightning. I'm just gonna really briefly, I got a few minutes. I'm gonna walk through our process flow a little bit for those geeks in here that are really interested in what we're doing at the process level. So it's a pretty long and involved we touch every single aspect of this sensor fabrication. And so we get the wafers receive them from the fabs. That's kind of an example wafer up in the far left. And then we have these probe testers that basically, this is critical for selecting good quality wafers, throwing out the bad eggs. And we have these little probe cards that have these fingers that touch all the contacts on the sensor before we've even done any work on it, and to check if it's a good sensor, functionality. We can even do imaging tests at cryogenic temperatures. We go through, we do send out, one of the few things that we actually send out, we send the sensors out the back. So these are all backside illuminated sensors because that improves the quantum efficiency and fill factors of our arrays. So we actually illuminate everything, image everything on the backside of the wafer, of the die. And so we essentially need to hybridize these on the substrates. And so this entire process is going through and doing that packaging. So we do gold stud bumps on the wafers. Then we dice out the wafers, cutting out that square from that large circle up you see in the corner. So once we have the die, we do this hybridization processing where we basically flip chip bond and to hybridize the array onto a substrate. The substrate is usually a silicon or ceramic that we have manufactured, that we work with the manufacturer to design that substrate. And so it's basically a fan out to take the bonds, take the contacts out so that we can put it on, attach it to a circuit board later on. And so this video is basically a process, shows that process of like you're literally squishing the wafer or the die onto the substrate with these contact bonds, these indium gold contacts, bumps, and the squish it into place. Next, we provide an epoxy underfill to keep mechanical support, because these things go in cryogenic temperatures, so you really want these a good support so things aren't breaking during the cooling process. And in the end, and so one of the critical things that we do is this acid etching on the backside to thin the device to exactly the thickness that we want, because that drives the wavelength sensitivity of the device. And we have special processes, and you can see there's a little video up in the corner showing this dunk process going on. So next, we continue on. We do an oxidation process, basically get rid of all these. I'm probably in the weeds for most of you people. I apologize, but to get these, get rid of some of the, to basically pacify it. And then we develop anti-reflective coatings, custom anti-reflective coatings, depending on what the customer or the instrument needs, UV, blue, red, different red coatings. And we have this really cool coating chamber that allows us to do various materials like hafnium, magnesium sulfide. Once we're through that with the coatings, we have metrology, to make sure to measure the flatness and positions of the array, the hybridized array, and well, we package, then we do metrology. Packaging is basically just putting it into a metal mount like Invar, and wire bonding the array to get array up. And then metrology and characterize, we have a lab for doing automatic characterizations, all these common tests, quantum efficiency, read noise, dark current, dynamic range, and that puts me at the end. So.
Thanks for the talk. It's told me that absorption will be the benefactors of your lab for many decades. And CCDs have been the detector of choice for over 3 decades now. What's the future?
Yes. I mean, it is kind of interesting. Everyone keeps talking about, oh, CCD is such an old technology. Why not? Why are we still using them? And I mean, the future is, I think, CMOS for sure. But CCDs still have a lot of value. I mean, currently we are working with LBNL, Fermilab, to do basically sub-electron read noise CCDs. So that's an exciting prospect for a lot of range of technology of astronomy programs, future, like even space programs, exoplanet discovery investigations. So I think there's still a lot of, these still have a lot of, so yeah, CCDs are still the future.
Yeah. I'm curious about your poker technology. Do you customize it in any particular way, or
The AR coding? Oh yeah, totally customized. So it really depends on what people want. We have, tantalum, hafnium, and magnesium sulfide are the 3 main coatings that we use. We could probably do different ones if someone really requested it. But we do custom layers, thicknesses on everything. It really depends on what the instrument requires. And there's been some, really great broadband coatings, like 80, 90% QE across like the red and blue